What if I told you the night sky you gaze up at, those scattered pinpricks of light, aren't just random stars and galaxies drifting alone in the dark? What if, hidden from plain sight, there's an invisible architecture weaving them all together, a cosmic skeleton holding the universe in place? This isn't science fiction, it's real, and it's called the cosmic web. Picture this: trillions of galaxies strung like beads on threads of dark matter and gas, stretching across billions of light years, forming a structure so vast it defies imagination. This web isn't just a backdrop, it's the universe's blueprint, shaping where stars are born, where galaxies collide, and even where we might find alien worlds. Now here's what's even wilder: we can't actually see this web with telescopes. It's made of dark matter, an enigmatic substance that doesn't emit light or energy, yet holds everything together with its gravitational pull. Think of it like the wind. You can't see it, but you feel its effects, bending trees and shaping landscapes. The cosmic web does the same for the cosmos, guiding galaxies into clusters and leaving empty voids between them. For decades, it was just a theory, a ghostly outline sketched by mathematicians. But today, cutting-edge technology is finally pulling back the curtain, giving us glimpses of this hidden framework. So how do you map something invisible? That's where things get thrilling. Scientists are using quasars, the universe's brightest lighthouses, to trace the web's faint shadows. Supercomputers simulate its structure down to the finest filaments, and new telescopes like the James Webb are peering deeper into space and time than ever before, uncovering clues about how this web shaped the universe from its earliest moments. This isn't just about understanding the stars, it's about unlocking the story of us, because every atom in your body was once part of this vast network, forged in galaxies spun from the cosmic web's threads. Ready to explore how we're unraveling the universe's greatest hidden structure? Let's dive in. The cosmic web is the backbone of everything we see and don't see in the universe. Imagine taking the most intricate spider's silk, magnifying it 1 billion times, and weaving it through the emptiness of space. That's essentially what this structure looks like, a vast network of glowing filaments, each one a highway of galaxies, gas, and dark matter stretching across unimaginable distances. But between these threads, enormous voids, cosmic deserts so empty that a single galaxy might be the only speck of light for millions of light years. It's not just a pretty pattern. This web dictates how the universe grows, how galaxies collide, even how planets like ours eventually form. What makes this even more mind-bending is how much of it remains hidden. Dark matter, the invisible glue holding the web together, doesn't interact with light, so we can't see it directly. But its gravitational pull is undeniable, sculpting galaxies into clusters and leaving those eerie voids in between. Think of it like an invisible hand shaping wet clay. You don't see the fingers, but their imprint is everywhere. And just like a neural network in the human brain, these filaments aren't random, they're information superhighways, channeling matter and energy to create the universe as we know it. This discovery turned astronomy upside down. For centuries, we pictured galaxies floating in isolation, adrift in black emptiness. Now we know they're nodes in a grand design, connected by threads of dark matter trillions of miles long. Even Einstein's theory of relativity couldn't predict this level of structure. It took supercomputers and sky-scanning telescopes to reveal the web's true scale. Every time we map a new section, it challenges what we thought possible. Some filaments are so long they shouldn't exist under our current physics. It's like finding a bridge spanning an ocean with no visible supports. Nature's way of reminding us how much we still have to learn. Dark matter is the universe's best-kept secret, an invisible force so powerful it outweighs everything we can see by a ratio of 5:1. If the cosmic web is a skyscraper, dark matter is its steel framework, unseen yet holding every floor in place. Without it, galaxies would fly apart and the web's delicate filaments would unravel into chaos. But here's the twist, we've never actually caught a single particle of it. It doesn't glow, reflect, or absorb light. It's like gravity's ghost, leaving fingerprints everywhere but vanishing the moment we try to look directly at it. So how do we know it's there? Imagine waking up to find your furniture mysteriously rearranged overnight. You didn't see anyone move it, but the evidence is undeniable. That's how scientists discover dark matter, by spotting its gravitational tug on the visible universe. Galaxies spin faster than they should, their stars clinging to the edges as if an invisible hand is gripping them tight. Light bends around cosmic voids, warped by something we can't see. Even the cosmic web structure, those sprawling filaments and empty voids, wouldn't exist without dark matter's gravitational blueprint. It's the unseen architect sketching the universe's design before a single star ignites. The hunt to understand this mysterious substance has led to some of astronomy's most creative detective work. Teams buried detectors deep underground, waiting for a rare collision between dark matter and ordinary atoms. Others tracked gamma rays flaring from galaxy clusters, potential clues of dark matter particles annihilating each other in space. And then there's the bullet cluster, a cosmic collision where galaxies and dark matter apparently separated, like two ghosts passing through each other, leaving visible matter trailing behind. These aren't just curiosities, they're proof that dark matter isn't some placeholder in our equations. It's as real as the gravity holding your feet to the ground. Yet for all its dominance, dark matter remains frustratingly elusive. Some theories suggest it's made of weakly interacting massive particles that barely touch ordinary matter. Others propose actions, particles so light they flit through space like cosmic whispers. But here's the kicker, if dark matter is everywhere, why haven't we felt it? Why doesn't it brush against your skin or pool in the corners of rooms? The answer lies in its weakness. A single dark matter particle could pass through a planet like a bullet through fog, never slowing, never stopping. It's not just invisible, it's untouchable. This paradox is what makes dark matter so thrilling and so vital to unraveling the cosmic web. Without it, the universe would look utterly different. No grand design, no galaxy clusters, perhaps no planets or life. Every time we map another strand of the web, we're tracing the shadow of something far stranger than we ever imagined. And the deeper we look, the clearer it becomes. Dark matter isn't just part of the cosmos. It is the cosmos humming silently beneath the surface of everything we know. Galaxy filaments are the universe's grandest bridges, stretching hundreds of millions of light years across the void, weaving galaxies together in shimmering strands. These aren't just cosmic decorations, they're the dense highways of the cosmic web, where galaxies gather like bustling cities along an interstellar freeway. Picture a necklace strung with pearls, except each pearl is a galaxy, and the necklace is longer than anything our minds can truly grasp, one of the most jaw-dropping examples. The Boss Great Wall, a filament so colossal it defies expectations, a staggering 1 billion light-years long. A structure so vast it shouldn't exist under our current understanding of the universe's limits. What makes these filaments so astonishing isn't just their size, but how they shape everything around them. Galaxies don't just float near these threads, they're pulled into them, drawn by the gravitational whisper of dark matter. Entire clusters merge and collide along these pathways, sparking bursts of star formation and birthing supermassive black holes. It's like watching rivers carve valleys, except the valleys are made of galaxies and the rivers flow with invisible dark matter. And just like rivers on Earth, these filaments aren't random. They converge at nodes where galaxy clusters pile up like cosmic intersections, buzzing with gravitational energy. Recent telescope surveys have peeled back even more layers of mystery. Some filaments glow faintly with hot gas, a ghostly tracer of the web's hidden architecture. Others seem eerily empty, as if the universe left deliberate gaps in its design. And then there's the shocker, astronomers have spotted galaxies moving along these filaments at breakneck speeds, surfing the gravitational currents like stars on a celestial conveyor belt. It's a revelation that's rewriting our playbook for how galaxies travel, not drifting aimlessly, but guided by the web's invisible hand. But here's the real kicker: these filaments might hold the key to the universe's expansion. Some theories suggest dark energy, the force ripping space apart, could be stretching these threads like taffy, thinning them over time. Others think the filaments themselves might be funneling mysterious particles we've yet to discover. Every new observation peels back another layer, revealing just how much we've underestimated the universe's scaffolding. These aren't just threads in the dark, they're the universe's DNA, encoding the story of how everything from the tiniest star to the largest cluster found its place in the cosmos. If galaxy filaments are the dense superhighways of the cosmic web, then the voids between them are the universe's silent deserts, vast, empty regions so colossal they could swallow thousands of Milky Ways without a trace. These aren't just gaps, they're staggering absences, some stretching over 100 million light-years, where galaxies are almost non-existent. Picture pouring a handful of sand onto a sheet of black paper. The grains cluster in some places, while elsewhere there's nothing but darkness. That's the cosmic void, an eerie nothingness sculpted by the same invisible hands of dark matter that weave the web's filaments. What's fascinating about these voids isn't just their emptiness, it's how they shape the universe around them. Like invisible bubbles in a cosmic foam, they push galaxies toward the filaments, herding them into the denser threads of the web. Imagine blowing on a pile of dust. The particles scatter, but they also gather along the edges of your breath's path. That's what voids do to galaxies, gentle but relentless, guiding them toward the crowded highways of the cosmic web. And here's the twist: this movement isn't random. The void's gravitational influence is so profound that astronomers can trace galaxy flows, watching as entire clusters drift toward denser regions, pulled by the absence of matter as much as its presence. Take the local void, a sprawling emptiness right on our cosmic doorstep, nudging the Milky Way and its neighbors toward the Virgo cluster like an unseen tide. It's a reminder that even our galaxy isn't floating freely. It's part of this grand choreography, dancing to the gravitational tune of both the web's threads and the voids between them. Scientists once thought these voids were truly empty, but recent observations hint at something stranger. A few lone galaxies, dubbed void galaxies, drift in these deserts, evolving in isolation, untouched by the collisions and bursts of star formation that shape their crowded cousins. These cosmic loners are like islands in an endless ocean, offering clues about how galaxies behave when left alone for billions of years, yet the most mind-bending revelation. Voids might hold secrets about dark energy, the mysterious force accelerating the universe's expansion. As space stretches, these voids grow even emptier, their edges thinning like soap bubbles in a windstorm. Some theories suggest dark energy's fingerprints could be etched into their growth, offering a new way to measure its influence. Others propose that voids themselves generate tiny ripples in spacetime, gravitational waves so faint we've yet to detect them. Every observation peels back another layer, revealing that these empty regions are anything but passive. They're dynamic, shaping the universe as much as the glittering filaments they border. So the next time you look up at the night sky, remember, the darkness between the stars isn't just empty space. It's part of an invisible architecture, a cosmic counterbalance to the web's glowing strands. Without these voids, galaxies wouldn't move, clusters wouldn't form, and the universe as we know it would look entirely different. They're the silent players in the grand story of the cosmos, proof that sometimes nothingness holds the deepest mysteries of all. The story of the cosmic web begins not with cutting-edge telescopes, but with a handful of bold thinkers staring at the night sky and daring to ask what's missing. In the 1930s, Swiss astronomer Fritz Zwicky noticed something bizarre about the Coma cluster. a group of galaxies over 300 million light-years away. The galaxies were moving too fast. According to Newton's laws, their gravity alone shouldn't have been enough to hold them together. They should have flown apart like sparks from a fire. Zwicky's conclusion, there had to be something invisible, something massive, binding them together. He called it Dunkel Materie, dark matter, a term that would haunt astronomy for decades. At the time, most scientists dismissed the idea. How could the universe be filled with matter we couldn't see? Telescopes back then were like peering through a foggy window, good enough to spot galaxies but blind to the threads connecting them. Without proof, Zwicky's theory languished like a ghost story. Then, in the 1970s, another visionary entered the scene, Richard Gott. Using early computer simulations, Gott proposed something radical. The universe wasn't just random galaxies floating in blackness, it was structured, with galaxies clumping along interconnected lines like a sponge's porous surface. His model showed empty voids bordered by dense walls, a cosmic lattice emerging from the Big Bang's chaos. But here's the catch, Gott's work was purely theoretical. The tech of the era couldn't confirm his sponge-like universe. Telescopes lacked the sensitivity to map faint filaments, and dark matter's shadowy nature made it impossible to detect directly. For years, the cosmic web remained a sketch in the margins of astrophysics, a beautiful idea waiting for tools precise enough to bring it into focus. It wasn't until the 1980s and 90s, with advances like redshift surveys and supercomputers, that the web's faint outline began to emerge. Suddenly, Zwicky's dark matter and Gott's sponge weren't just speculation. They were the hidden blueprint of reality itself. What's striking about this journey is how much of science hinges on patience and imagination. Zwicky and Gott didn't just lack data, they lacked the language to describe what they sensed. Today, we take the cosmic web for granted, but back then, it was like predicting the internet while still using Morse code. Their theories were cracks in the door, glimpses of a truth far stranger than anyone expected. And now, as we map the web's filaments with tools like the James Webb Space Telescope, we're not just proving them right, we're stepping into the universe they imagined long before we could see it. To unravel the cosmic web's hidden design, scientists turn to the most powerful tools we have, not telescopes, but supercomputers. These machines don't just crunch numbers, they rebuild the universe. Take NASA Pleiades supercomputer, a beast capable of performing quadrillions of calculations per second. It's like handing an artist a brush the size of a city, except instead of paint, they're using the laws of physics to simulate how dark matter sculpted the cosmos from the Big Bang to today. The result, stunning, high-definition visualizations of the cosmic web emerging like a time-lapse of a growing neural network, filaments threading through the void in a dance older than time. At the heart of these simulations are N-body models, mathematical playgrounds where millions, even billions of virtual particles stand in for dark matter. Each particle obeys gravity's pull, clumping together or drifting apart over billions of simulated years. The magic happens when scientists hit play. Particles swarm into filaments, clusters, and voids, mimicking the real universe's structure with eerie accuracy. It's like dropping sand onto a vibrating plate and watching it self-organize into intricate patterns, except the plate is space-time, and the sand is the unseen scaffolding of reality. Some of the most jaw-dropping simulations reveal the universe's adolescence, a turbulent era around 2 billion years after the Big Bang. Here, dark matter's tendrils begin condensing, pulling gas along for the ride until it ignites into the first galaxies. These fledgling stars don't light up randomly, they spark along the filaments as if the cosmic web is a celestial circuit board powering the universe. And the simulations don't just show us the past, they predict the future. Run the clock forward and you'll see the web stretching further, voids growing emptier as dark energy pushes the universe toward an ever more diffuse fate. But these models aren't flawless. The universe, it turns out, is messier than any simulation. tiny discrepancies like how fast galaxies spin within filaments hint at gaps in our understanding. Maybe dark matter isn't the only player. Perhaps unknown forces tweak the web's threads. That's why teams constantly refine their code, feeding in new data from telescopes like the James Webb to cross-check their virtual cosmos against the real thing. Every tweak unveils fresh surprises, like filaments that shouldn't be as twisted as they are, or voids that defy expectations by attracting galaxies instead of repelling them. What's truly groundbreaking is how these simulations bridge theory and observation. When astronomers spot a distant galaxy cluster, supercomputers can rewind its history, tracing how it rolled along the cosmic web's highways to reach its place in the sky. They've even revealed missing filaments too faint for telescopes to detect, ghostly strands confirmed only because the models said they had to be there. It's a cosmic detective story where the clues are written in gravity's invisible ink, and supercomputers are the magnifying glass. So next time you see a visualization of the cosmic web, remember, those glowing filaments aren't just artist renditions. They're the product of humanity's most ambitious thought experiment, a universe reborn inside a machine, helping us decode the dark skeleton holding everything together. The Sloan Digital Sky Survey didn't just map the stars, it rewrote our cosmic address book. Imagine painstakingly cataloging every city on Earth, then realizing they're all connected by invisible highways. That's what SDSS achieved on a galactic scale, capturing precise 3D positions for over 3 million galaxies across a quarter of the night sky. Its telescope in New Mexico didn't just snap pretty pictures, it dissected starlight like a prism, measuring redshifts to calculate each galaxy's distance with pinpoint accuracy. The result, the universe's first massive 3D atlas, revealing the cosmic web's architecture in strokes so bold they stunned even seasoned astronomers. One of SDSS' most dazzling discoveries was just how textured the universe really is. Earlier sky surveys saw galaxies as random sprinkles in the cosmic dark. But SDSS maps showed them clinging to filaments like dew on a spiderweb, with voids yawning between them like black oceans. One filament, dubbed the Sloan Great Wall, stretched over 1.4 billion light-years, a structure so colossal it challenged theories about how large the universe's building blocks could grow. And here's the kicker, this wasn't just a snapshot. By observing galaxies at different distances, SDSS effectively built a time machine, showing how the web evolved over billions of years as dark matter's gravity stitched galaxies into ever denser threads. Behind these revelations was a data tsunami. SDSS telescope gathered so much information, equivalent to 500,000 DVDs, that it forced astronomers to invent new ways to store and analyze cosmic data. Every night, its camera captured 1.5 terabytes, enough to fill a library with raw numbers. But the real magic happened when supercomputers chewed through this mountain of digits, transforming them into visualizations that made the invisible web pop for the first time. Suddenly, theorists could test their simulations against real filaments, voids, and clusters, cross-checking whether their dark matter models held up. Spoiler, they did, but with quirks like mysterious dark flows, where galaxies seem to move toward unseen mass beyond the observable universe. Perhaps SDSS' quietest revolution was how it democratized space exploration. Unlike elite telescopes hogged by a handful of scientists, SDSS data was, and still is, free for anyone to explore. Amateur astronomers have discovered dwarf galaxies in its archives. High school students have tracked galaxy collisions. It even birthed Galaxy Zoo, a crowdsourcing project where over 100,000 volunteers helped classify galaxies online, proving you don't need a PhD to contribute to cosmic cartography. The survey's legacy isn't just in maps, it's in shifting how we see the universe. Before SDSS, the cosmic web was an elegant hypothesis. After an undeniable reality, its filaments etched across petabytes of data. Future telescopes like the Vera Rubin Observatory owe their blueprints to SDSS pioneering scans because sometimes to grasp the universe's grand design, you first need to count every brushstroke. To uncover the cosmic web's faintest threads, astronomers turn to one of nature's most brilliant flashlights, quasars. These ultra-bright beacons, powered by supermassive black holes, shine with the intensity of 1 trillion suns, casting their light across billions of light years. But it's not just their raw power that makes them invaluable, it's what happens to their light on its journey through the web's hidden gas. Picture sunlight filtering through a dense forest, where every leaf absorbs a tiny fraction of the beam, leaving a pattern of shadows on the ground below. That's essentially how quasars reveal the cosmic web's finest details through an effect called the Lyman alpha forest. Here's how it works. As quasar light travels toward Earth, it passes through clouds of hydrogen gas strung along the web's filaments. This gas absorbs specific wavelengths of light, particularly in the ultraviolet range known as the Lyman alpha line. Each cloud acts like a cosmic filter, imprinting a unique fingerprint of absorption lines on the quasar spectrum. The result, a barcode of dark spikes, each one a record of hydrogen encountered along the path. Some spikes are deep and narrow, betraying dense knots of gas. Others are shallow and broad, hinting at wispy filaments too faint to see directly. Together, they form a forest of absorption lines, a delicate tracer of the web's hidden skeleton. What's wild about this technique is its precision. By analyzing these absorption lines, astronomers can pinpoint the gas's temperature, density, and even its motion. Some clouds are racing toward us, their lines shifted slightly blue. Others drift away, their signals stretched red. It's like listening to the Doppler effect in a cosmic rainstorm where every drop's pitch reveals its speed and direction. And just like rain soaks into soil, these hydrogen clouds trace the web's distribution, highlighting filaments that would otherwise vanish into the void. The real breakthrough came when scientists realized they could stack multiple quasar spectra, combining their absorption lines to map the web's large-scale structure. Imagine reconstructing a city's skyline by studying only the shadows cast by distant street lamps. That's the level of cosmic detective work involved. Some of the most stunning maps reveal tendrils of gas stretching between galaxy clusters, proof that the web's filaments aren't just theoretical. They're real, measurable highways of matter woven through the universe's emptiest realms. But the Lyman alpha forest isn't just a map, it's a time capsule. Because light takes billions of years to reach us, each quasar's spectrum captures a snapshot of the web at a different cosmic era. Younger forests show thicker, more chaotic absorption lines, reflecting a time when gas was still clumping into filaments. Older ones appear more refined, their lines smoothed by eons of gravitational tugging. This lets astronomers watch the web mature from its messy infancy to the elegant scaffold we see today. Of course, there are puzzles. Some regions show too much absorption, hinting at gas clouds colder or denser than models predict. Others appear suspiciously empty, as if something, perhaps dark energy, has been clearing them out over time. These anomalies are gold mines for new physics, challenging our assumptions about how the web evolves. And with next-gen telescopes like the 30-meter telescope set to analyze fainter quasars, we're on the verge of mapping the web's thinnest strands, threads so delicate they might finally reveal the universe's most elusive secrets. So next time you hear about quasars, don't just think of them as distant lighthouses. They're cosmic scribes etching the story of the web's invisible ink into their light, one absorption line at a time. Gravity doesn't just pull, it bends. Imagine space as a trampoline with galaxies and dark matter pressing down like bowling balls, warping the fabric beneath them. Now picture a marble rolling across that distorted surface. Its path wouldn't be straight. It would curve, following the dips and slopes. That's exactly what happens to light traveling through the cosmic web. When beams from distant galaxies pass near massive filaments or clusters, they don't sail straight to our telescopes. They bend, twisted by the web's invisible gravity in a phenomenon called gravitational lensing. It's Einstein's general relativity in action. Mass warps spacetime, and spacetime tells light how to move. The Hubble Space Telescope has turned this cosmic quirk into one of our sharpest tools for mapping the unseen. When Hubble captures a galaxy cluster, it doesn't just show the galaxies themselves. It reveals their distorted halos, stretched into arcs and rings like reflections in a funhouse mirror. These aren't flaws in the image, they're clues. By measuring how much the light bends, astronomers can calculate the mass responsible for the distortion, including the dark matter hiding between the stars. Some of Hubble's most iconic shots, like the Hubble Frontier Fields, showcase this perfectly. Galaxies smeared into crescent shapes around massive clusters, their light twisted by the web's hidden scaffolding. But Hubble isn't working alone. Projects like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are pushing lensing to new extremes. They're not just looking for dramatic arcs, they're detecting subtle distortions, where millions of galaxies appear slightly stretched, their shapes aligned like iron filings near a magnet. This weak lensing effect is fainter but far more pervasive, betraying the presence of diffuse dark matter filaments too tenuous to create obvious bends. Combine enough of these tiny distortions, and suddenly the cosmic web's ghostly outline snaps into focus, traced by the warped light of billions of galaxies. Here's what's truly mind-blowing. Lensing doesn't just reveal the web's structure, it lets us weigh it. By analyzing how severely light bends, scientists can calculate exactly how much dark matter lurks in a given filament or cluster. Some strands contain thousands of times more mass than their visible galaxies suggest, a testament to dark matter's dominance. And because lensing works at all distances, it's like a universal scale, weighing the web's components near and far, from today's universe back to when it was half its current age. The most astonishing lensing discoveries aren't just about mass, though. They're about missing mass. Certain regions bend light more than they should, hinting at invisible structures, perhaps unknown particles, or even alternate dimensions tugging at the fabric of space. Other areas show lensing patterns that suggest dark matter might interact with itself in ways we never predicted, clumping differently than standard models allow. Every distorted galaxy is a puzzle piece, and when we fit them together, the picture that emerges is far stranger than Einstein ever imagined. So the next time you see a photo of a warped galaxy, remember, you're not just looking at light. You're seeing space itself twisted into knots, a cosmic fingerprint left by the invisible hand of the web. And with every new lensing map, we're not just tracing dark matter, we're reading the universe's hidden diary, one bent beam of starlight at a time. In 2020, cosmology got its most detailed timeline yet, a map stretching across 11 billion years of cosmic history. The Extended Baryon Oscillation Spectroscopic Survey, or EBOS, didn't just add another layer to our understanding of the cosmic web. It revealed how the universe's expansion accelerated in fits and starts, like a car with an invisible foot alternating between the gas and brake. For the first time, we could see the web's growth spurt during its teenage years, a chaotic era when dark energy began overpowering gravity's pull. At the heart of EBOS revelations were baryon acoustic oscillations, ghostly ripples frozen into the fabric of space. Picture the aftermath of a stone dropped in a pond, except the pond is the early universe, and the ripples are pressure waves from the Big Bang's first moments. These waves left an indelible fingerprint, a preferred distance between galaxies, like cosmic breadcrumbs tracing how the web stretched over time. EBOS measured this distance across millions of galaxies, comparing ancient structures to modern ones. The result, a high-precision yardstick showing exactly when dark energy kicked into high gear, flinging the web's filaments apart faster than anyone predicted. One of EBOS' most startling finds was how lumpy the young universe was. Maps of the web 11 billion years ago show thicker filaments and smaller voids, like a sponge not yet fully expanded. As dark energy took hold, those voids ballooned, stretching the web's threads into the delicate filaments we see today. But here's the twist: the expansion wasn't smooth. Some regions accelerated faster, as if dark energy's grip was stronger in certain directions. A mystery that's still shaking up cosmology. The survey also tackled one of astronomy's biggest headaches, the Hubble tension. Depending on where you look, the universe's expansion rate seems to disagree by a hair. EBOS data hinted that dark energy might not be constant. It could evolve, growing stronger or weaker over time. That would rewrite textbooks overnight, turning dark energy from a static force into something dynamic, almost alive in its influence. But EBOS legacy isn't just in answers, it's in questions. Why do some filaments resist dark energy's push, holding galaxies tighter than models allow? Could there be a hidden connection between dark energy and dark matter, two mysteries conspiring to shape the web? Every data point is a thread in a larger puzzle, one that next-gen telescopes like DAISY are now racing to solve. This isn't just about distant galaxies. It's about destiny. The cosmic web's expansion dictates whether, billions of years from now, new stars will still ignite, or if the universe will fade into a cold, threadbare silence. EBOS gave us the first clear snapshot of that struggle, a front-row seat to the tugs of war sculpting reality itself. Picture a telescope so precise it can measure a galaxy's movement from the other side of the universe, then multiply that by 35 million. That's the Dark Energy Spectroscopic Instrument, or DAISY, currently perched atop a desert mountain in Arizona, quietly rewriting the rules of cosmic cartography. Unlike traditional telescopes that snap pretty pictures of the sky, DAISY mission is laser-focused. It's mapping the cosmic web in 3 dimensions with unprecedented detail, using a staggering array of 5,000 tiny robotic eyes. Each one can lock onto a galaxy or quasar in under 20 seconds, measuring its light so precisely, we can trace its place in the web's grand design down to a millimeter per second of motion. The goal: to solve the universe's biggest tug of war, the battle between dark matter's gravity and dark energy's relentless push. What makes DAISY revolutionary isn't just its scale, it's its speed. Previous surveys like SDSS took decades to map a fraction of the sky. DAISY, with its army of robotic fibers, can chart millions of galaxies in a single year. Each night, its lenses swivel autonomously, repositioning all 5,000 fibers onto new cosmic targets like a grand celestial ballet. The result: a time-lapse of the universe's expansion, stretching from today back to when galaxies first huddled along the web's primordial threads. But DAISY's real power lies in its targets, not just galaxies, but quasars, those brilliant beacons whose light pierces the web's hidden gas. By analyzing how this light bends and dims, DAISY can trace dark matter's distribution in the emptiest voids, filling in the web's faintest gaps. And here's the kicker: it's not just mapping the web's present. By comparing distant quasars whose light left billions of years ago to nearby galaxies, DAISY essentially captures before and after snapshots of the web's evolution, letting us watch in real cosmic time as dark energy stretches its filaments like taffy. The instrument's most tantalizing promise: cracking dark energy's code. Right now, we treat it as a constant force, but what if it changes over time? DAISY ultra-precise measurements could reveal tiny speed bumps or dips in the universe's expansion, hints that dark energy isn't the steady void filler we assumed. Some theories suggest it might grow stronger, eventually shredding the web's threads entirely. Others propose it could flicker, its influence waxing and waning like cosmic seasons. DAISY data might even uncover whether dark energy interacts with dark matter, a possibility that could unify the universe's 2 greatest mysteries into a single, elegant framework. Already, early DAISY maps have delivered surprises. Certain galaxy flows defy expectations, as if tugged by invisible superstructures beyond our view. Filaments appear slightly warmer than models predicted, hinting at unknown physics heating the web's gas. And then there's the Hubble tension, the stubborn mismatch in the universe's expansion rate. DAISY measurements could finally settle the debate, revealing whether the discrepancy stems from measurement errors or something far stranger, like an undiscovered particle subtly tweaking gravity's rules. This isn't just about mapping the cosmos, it's about decoding fate itself. Will the web's filaments snap, leaving galaxies adrift in an ever-expanding void? Or will dark energies grip loosen, allowing gravity to weave new structures we can't yet imagine? DAISY robotic eyes are staring down these questions, one galaxy at a time, and with every new data point, we're not just reading the universe's story. We're glimpsing its final chapter. The future of cosmic mapping no longer rests in human hands alone. It's being reshaped by artificial intelligence, trained to see patterns in the chaos that even our sharpest minds might miss. Take Google's DeepMind, a system originally designed to master complex games like Go. Astronomers handed it a new challenge: decipher the cosmic web's tangled threads from the blur of telescope data. The results were staggering. By analyzing subtle distortions in galaxy shapes and light patterns, the AI pinpointed dark matter filaments with 99% accuracy, threads so faint they'd slipped past decades of human analysis. It's like giving a detective ultraviolet goggles in a pitch-black room, revealing fingerprints no one knew were there. How does it work? Machine learning thrives on patterns. Feed it enough simulations of the cosmic web, how dark matter clumps, how gas flows, and it begins recognizing those blueprints in real observational data. Traditional methods rely on painstaking manual measurements, like counting tree rings to gauge a forest's age. AI, though, takes in the entire forest at a glance, spotting connections invisible to the naked eye. Some algorithms have even begun predicting filament locations before telescopes confirm them, essentially drafting maps of the unseen based on gravitational whispers. But here's where it gets eerie. In 2023, an AI trained on Sloan digital sky survey data uncovered a filament stretching between two galaxy clusters, a structure astrophysicists had overlooked because it didn't fit expected models. The machine had no biases, no preconceived theories. It simply followed the data, revealing a cosmic thread that defied textbook logic. This isn't just about efficiency, it's about discovery. AI is becoming astronomy's intuition, flagging anomalies that could rewrite our understanding of dark matter's behavior. The revolution doesn't stop at mapping. Neural networks are now simulating the web's evolution, compressing billions of years into hours. Where supercomputers once took months to model a single filament's growth, AI can generate plausible cosmic histories in real time, testing how tweaks to dark energy or particle physics alter the web's weave. It's like having a universe-sized sandbox where scientists adjust gravity's strength or dark matter's stickiness, then watch the cosmic consequences unfold. Yet for all its brilliance, AI has limits. These systems can't explain why they make certain connections their cosmic oracles, spitting out answers without revealing their logic. That's where humans and machines converge. Astronomers use AI's predictions as treasure maps, then deploy telescopes like James Webb to dig for physical proof. Together, they're peeling back layers of the web we once thought were forever out of reach. The implications ripple far beyond our own galaxy. If AI can decode the cosmic web's blueprint, it might finally answer why some filaments are denser, why voids grow emptier. Clues hidden in data too vast for any team of scientists to sift alone. This isn't just a new tool, it's a new lens sharpening our view of the universe's deepest architecture. And with every filament traced, every void measured, we're not just mapping the cosmos. We're teaching machines to see its secrets and in turn, learning how much we've yet to discover. Some of the most tantalizing clues about the cosmic web might come from particles so elusive they slip through entire planets like ghosts through walls. Neutrinos, tiny, nearly massless particles born in violent cosmic events, rarely interact with matter, making them astronomically hard to detect. But that very aloofness is what makes them perfect messengers from the web's densest, most chaotic regions. When a high-energy neutrino finally does collide with an atom in a detector, it's like intercepting a cosmic telegram, carrying intel from places even light can't easily escape. Like the hearts of galaxy clusters or the turbulent borders of supermassive black holes. Enter DUNE, the Deep Underground Neutrino Experiment, a next-generation detector currently taking shape beneath the South Dakota plains. Unlike traditional telescopes that rely on light, DUNE colossal tanks of liquid argon will sit a mile underground, waiting for the rare flash of energy when a neutrino strikes. Why go to such lengths? Because ultra-high-energy neutrinos don't just travel through the cosmic web, they're shaped by it. As these particles race across the universe, their paths subtly bend around filaments of dark matter, and their energies shift when traversing vast voids. By analyzing these changes, scientists can reconstruct the web's hidden topography, much like tracking seismic waves to map Earth's interior. Here's the twist: neutrinos might be the only particles that can directly probe cosmic voids. These empty regions are so devoid of matter that traditional methods like observing gas or starlight hit dead ends. But neutrinos, indifferent to the absence of atoms, sail straight through, emerging with tiny scars from their journey. Some theories suggest voids could even trap certain neutrino types, creating cold spots in the particle flow that DUNE might detect. It's like listening for echoes in a cave. The silence itself becomes a clue. DUNE isn't flying solo. IceCube, a detector buried in Antarctic ice, has already spotted neutrinos from beyond our galaxy, some with energies 1,000,000 times greater than LHC collisions. One infamous particle, nicknamed Big Bird, packed enough punch to suggest it originated near a supermassive black hole, possibly within one of the web's densest nodes. Future upgrades aim to pinpoint these cosmic accelerators with even sharper precision, tracing them back to specific filaments or clusters, but the real prize. Neutrinos could reveal how the web's filaments funnel matter into galaxy clusters, or how turbulence at their edges generates particle shocks. Some models predict neutrino shadows around dense filaments, subtle dips in detection rates that betray dark matter's grip. Others speculate that neutrinos might decay differently in voids, hinting at undiscovered physics. Every interaction is a breadcrumb, leading us deeper into the web's most enigmatic corners. So while telescopes paint the cosmic web in broad strokes, neutrinos could fill in the fine details: the density of a filament's core, the magnetic fields threading a void, even the quantum ripples left over from the Big Bang. They're the universe's stealth scouts, slipping past barriers to deliver secrets no other particle can. And with detectors like DUNE coming online, we're not just waiting for messages from the dark. We're learning how to listen. Quantum computing could be the key to cracking the cosmic web's deepest mysteries, problems so complex they'd take classical supercomputers millennia to solve. Picture trying to untangle a spider's web with your bare hands versus using a swarm of nanobots that can manipulate every thread simultaneously. That's the power of quantum mechanics applied to cosmology. Unlike binary bits that process information as zeros and ones, quantum bits, or qubits, exist in multiple states at once, allowing them to simulate the web's tangled filaments, dark matter's ghostly pull, and even the universe's quantum origins in ways no conventional computer can match. CERN, the powerhouse behind the Large Hadron Collider, is already pioneering this fusion of quantum tech and cosmic mapping. Their quantum technology initiative explores how qubits might simulate conditions in the early universe, where the cosmic web's first threads condensed from a soup of particles and energy. One experiment focuses on modeling dark matter's behavior at microscopic scales, testing whether hypothetical particles like actions could form the web's invisible scaffold. The challenge: dark matter's quantum interactions, if they exist, are too subtle for today's detectors to spot, but a quantum computer could recreate them virtually, probing scenarios where dark matter particles collide, decay, or even generate faint radiation as they weave through filaments. The potential breakthroughs don't stop there. Google's quantum AI team recently demonstrated how quantum algorithms could optimize galaxy surveys, pinpointing the most efficient paths for telescopes to map the web's largest structures. Meanwhile, startups like Zapata Computing are training quantum neural networks to predict filament formation, feeding them data from telescopic observations and particle colliders. These hybrid systems learn like a human brain but process information at speeds that leave supercomputers in the dust, revealing patterns in the web's growth that were once invisible. What makes quantum simulations so revolutionary is their ability to handle uncertainty. The cosmic web isn't a static blueprint. It's a probabilistic tapestry where particles exist in flux until observed. Classical computers struggle with this nuance, forced to approximate probabilities. Quantum machines, though, thrive in ambiguity. They can simulate the universe as a series of overlapping possibilities, much like Schrödinger's famous cat alive and dead until the box opens. Applied to cosmology, this means modeling how filaments might have branched under different initial conditions, or how dark energy's push could vary across alternate realities. Yet quantum computing's cosmic role isn't just about raw power, it's about asking new questions. Could entangled qubits mimic the web's large-scale quantum correlations, where particles separated by billions of light-years somehow know each other's states? Might quantum gravity, still a theoretical puzzle, leave faint fingerprints in the web's voids? Projects like CERN are betting on it, designing experiments to test whether spacetime itself has a quantum code that the cosmic web obeys. The road ahead is thorny. Qubits are notoriously fragile, error-prone, and confined to near absolute zero temperatures. But as quantum error correction improves, so does the promise of a universe decoded. Imagine a day when these machines simulate not just slices of the web, but its entire evolution. From the first quantum ripples after the Big Bang to the last fading strands in a dark energy-dominated future. That's the horizon quantum cosmology is racing toward, not just mapping the universe's skeleton, but understanding the quantum heartbeat that makes it pulse. Galaxy Zoo turned astronomy on its head by proving something extraordinary. You don't need a PhD or $1 million telescope to rewrite cosmic maps. This crowdsourcing phenomenon, launched in 2007, invited anyone with an internet connection to become a galactic explorer, classifying galaxies from the Sloan Digital Sky Survey with a simple click. The response was staggering. Over 250,000 volunteers, teachers, truck drivers, even middle schoolers dove into the data, sorting spiral arms from elliptical blurs faster than any algorithm. But what started as a labeling project quickly became a revolution. Within days, users spotted something strange, tiny, glowing objects the color of emeralds, unlike anything in the textbooks. Dubbed green pea galaxies, these weren't just oddities, they were cosmic toddlers, birthing stars at rates 100 times faster than the Milky Way. Professional astronomers had scanned the same images for years and missed them. It took fresh eyes to see the universe anew. The magic of Galaxy Zoo lies in its simplicity. Each volunteer views a galaxy image and answers basic questions. Does it have spiral arms? Is it smooth or lumpy, merging with another? What sounds like a game uncovers patterns algorithms can't grasp. Humans excel at spotting the unexpected, a smudge that hints at a collision, a wisp betraying an unseen filament. One volunteer, Dutch schoolteacher Hanny van Arkel, stumbled on a glowing gas cloud so peculiar it earned its own name, Hanny's voorwerp. Later confirmed as a quasar's ghostly echo, it revealed how black holes flicker on and off over millennia. Another team of amateurs uncovered a galaxy missing its dark matter, a find that shook theories about how galaxies form. But the real triumph, mapping the cosmic web's finest threads. By classifying millions of galaxies, volunteers traced subtle alignments clusters strung along invisible filaments, their orientations betraying dark matter's pull. Some users even tagged faint bridges between galaxy clusters, later confirmed by telescopes as the web's gossamer strands. This wasn't just busy work, it was discovery. When professionals combined these classifications with supercomputer models, the web's map gained resolution no telescope could achieve alone. Galaxy Zoo's legacy isn't just in data. It's in democratizing wonder. A retiree in Wisconsin helped identify a new galaxy type. A teenager in India flagged a rare merging pair. Every click wove another thread into humanity's collective understanding of the cosmos. Today, projects like Zooniverse Galaxy Zoo's successor let anyone hunt for supernova, track Martian dust storms, or scan for exoplanets. The message is clear: the universe isn't just for experts. Its secrets hide in plain sight, waiting for anyone willing to look. And sometimes the next breakthrough isn't in a lab, it's on a laptop, halfway across the world, where someone's curiosity clicks submit. The cosmic web isn't just a backdrop for galaxies, it's their nursery, their lifeline, and the invisible hand guiding their very existence. Picture those vast filaments of dark matter and gas not as static threads, but as cosmic rivers flowing with the raw ingredients for star formation. Where these rivers converge, galaxies drink deeply, growing from scattered stardust into the glittering metropolises we see today. Take our own Milky Way, nestled along the outskirts of the Laniakea supercluster, a staggering network of 100,000 galaxies stretching over 500 million light-years. Like a city built at the intersection of ancient trade routes, our galaxy owes its position and its prosperity to the web's gravitational currents. Here's how it works. Primordial hydrogen, the universe's oldest fuel, gets funneled along filaments by dark matter's pull. As these gas streams collide near filament intersections, they compress, heat up, and ignite into stars. It's not unlike water cascading down mountain valleys, pooling into lakes where life blossoms. The densest knots become galaxy clusters, bustling hubs like Virgo, while quieter stretches spawn isolated galaxies like our own. But the Milky Way didn't form in isolation. Studies of its oldest stars reveal they're made of materials swept here by ancient filament flows, cosmic delivery trucks, hauling the atoms that would one day become our sun, our planet's us. Laniakea Hawaiian for immeasurable heaven is a perfect case study. This supercluster isn't a random swarm of galaxies, it's a web within the web, its members strung along intricate filaments like pearls on a necklace. At its heart lies the Great Attractor, a gravitational anomaly pulling everything in its reach, including the Milky Way at millions of miles per hour. This motion isn't random drift, it's the web's choreography. Just as rivers shape landscapes by carving canyons and depositing silt, these filaments sculpt galactic ecosystems, directing where and when stars burst to life. Recent simulations show something even wilder. Galaxies don't just form along filaments, they communicate through them. Thin tendrils of gas, too faint to see directly, act as cosmic supply lines, feeding galaxies long after their initial birth. Some astronomers compare it to an umbilical cord, continuously channeling fresh hydrogen to fuel new generations of stars. Without this replenishment, galaxies would starve, burning through their gas reserves in a cosmic blink. That's why the Milky Way's outskirts still sparkle with young stars. Filaments keep delivering gifts even now. But the web's influence isn't just about abundance, it's about timing. During the universe's cosmic noon, around 10 billion years ago, filaments were fire hoses of gas, birthing galaxies at a frenzied pace. Today, the flows are thinner, the star making slower. Yet in regions where filaments still overlap, like the Laniakea's bustling core, galaxies continue to feast, growing larger and brighter than their isolated peers. It's a reminder that location is everything, whether you're a star, a galaxy, or a supercluster riding the web's eternal currents. So the next time you gaze at the Milky Way's haze across the night sky, remember, you're not just looking at stars. You're seeing the aftermath of cosmic rivers that flowed billions of years ago, their waters still swirling in the veins of every atom in your body. The web didn't just build galaxies, it set the table for life itself. Black holes, the universe's ultimate gravitational traps, might also be its master architects, lurking at the hearts of almost every galaxy. Supermassive black holes don't just consume matter, they sculpt the very fabric of the cosmic web. Recent studies reveal these cosmic behemoths aren't randomly placed. They align like pearls on a string, their positions pinpointing where the web's densest filaments intersect. It's as if the universe threaded them there deliberately, turning black holes into gravitational anchors that stabilize entire swaths of the cosmic structure. The evidence comes from their jets, twin beams of plasma shooting outward at nearly light speed. In 2023, the Chandra X-ray Observatory made a startling discovery. These jets don't fire aimlessly. They consistently orient along nearby filaments, like compass needles pointing to hidden roads in the dark. One survey of over 800 galaxies found 70% of their black hole jets aligned within 30 degrees of the local filament's axis. That's no coincidence. It suggests the web's structure directly influences or is influenced by these monstrous objects, locking them into a cosmic choreography that spans billions of years. How does this work? Picture a black hole as a spinning top placed on a taut bedsheet. As it rotates, it drags space-time around it, creating whirlpools that tug on nearby matter. Now imagine that bedsheet is a filament of the cosmic web, channeling gas and galaxies toward the black hole like water down a drain. The incoming matter doesn't just vanish, it's hurled back out as jets, their direction steered by the filament's flow. Over eons, this feedback loop reinforces the web's architecture, with black holes acting like cosmic looms, weaving threads tighter while stitching galaxies into place. The implications rewrite our understanding of galactic evolution. Black holes were once seen as disruptive forces, belching radiation that sterilizes their surroundings. Now we know they're also regulators, their jets pumping energy back into filaments to prevent runaway star formation. Too many new stars, the jets heat the gas, slowing collapse. Too few, the black hole's gravity compresses fresh fuel, sparking stellar nurseries. It's a delicate balance, one that might explain why galaxies in dense filaments grow so much faster than their isolated cousins. But the real mind-bender, this alignment could be a relic from the universe's infancy. Simulations show the first black holes likely formed where dark matter filaments first crossed, gorging on the dense gas pooling there. Their growth and spin axes became locked to these primordial flows, preserving a fossil record of the web's birth. Today, when we trace their jet directions, we might be glimpsing the universe's original blueprint, the ghostly handshake between gravity's architects and the dark threads they've shaped for 13 billion years. This partnership between black holes and the web isn't just about structure, it's about survival. Without these anchors, filaments might dissolve, galaxies would drift apart, and the cosmic tapestry we see today would unravel into chaos. So the next time you hear about a black hole's destructive power, remember, it's also a cosmic keystone holding the universe together one thread at a time. The cosmic web isn't just a map of the universe, it's a time machine. Every thread of light reaching us from distant filaments carries a message from the past, a snapshot of how the universe looked when that light began its journey billions of years ago. When we peer at a galaxy cluster 10 billion light-years away, we're not seeing it as it is today. We're witnessing its infancy, a cosmic baby picture frozen in time. This is astronomy's greatest magic trick. The farther out we look, the deeper into history we gaze. and the web's filaments strung across the void like strings of pearls are the ultimate timeline, chronicling the universe's growth from a chaotic infancy to the ordered vastness we know now. Take the Lyman alpha forest, those absorption lines in quasar light we discussed earlier. Each dip in the spectrum isn't just a cloud of hydrogen, it's a timestamp. A filament 12 billion light-years away shows up as a dense thicket of absorption lines, its gas clumpy and turbulent, reflecting a younger, more violent universe. Compare that to a nearer filament whose smoother lines tell the story of eons of gravitational settling, like waves calming after a storm. By stacking these cosmic breadcrumbs, astronomers can trace how filaments evolved, from thin, knotted strands in the early universe to the fat, well-fed rivers of matter we see today. But the web's time-traveling secrets don't stop there. Some filaments act like cosmic zoetropes, their motion frozen in sequential frames. The Hubble Space Telescope once caught a filament 7 billion light-years away in the act of feeding a galaxy cluster, a process that would take millions of years to unfold. But because we're seeing it as it was 7 billion years ago, and nearby structures as they were 6 billion years ago, we can stitch together a flipbook of galactic growth. It's like finding a dinosaur's footprints leading to its bones. The web preserves its own history in light and shadow. Even the voids between filaments whisper secrets from the past. Distant voids are smaller and more crowded, like bubbles in a freshly poured soda. Nearby voids, by contrast, have expanded into vast emptiness, their edges stretched by dark energy. By measuring how much these cosmic bubbles have grown, we can clock the universe's expansion rate across epochs, a critical clue in the dark energy puzzle. The most mind-bending revelation: some filaments we see might not even exist anymore. A structure 11 billion light-years away, dazzling us with its youthful glow, could have long since dissolved into the web's quieter currents, its galaxies scattered by collisions or drained by voracious black holes. We're not just looking back in time, we're ghost hunting, tracing the echoes of a universe that's already moved on. This is why mapping the cosmic web isn't just about charting space. It's about rewinding the greatest story ever told, one photon at a time. Every observation is a puzzle piece in a billion-year saga, showing us how chaos birthed order, how emptiness shaped abundance, and how the threads of darkness stitched together the stars we call home. What if the cosmic web isn't just the scaffolding of our universe, but a fingerprint of something far stranger? Among the wildest theories in cosmology is the idea that those vast filaments and voids might hold clues to realities beyond our own, parallel universes brushing up against ours like shadows on a cave wall. In string theory, our universe could be a three-dimensional brain floating in a higher dimensional space, with other brains, other universes hovering just out of reach. Occasionally, these brains might collide, sending shockwaves rippling through space-time. And the aftermath: some physicists speculate that the cosmic web's most colossal filaments, the ones that defy expectations with their sheer size and alignment, could be the cosmic bruises left by these unimaginable impacts. Take the Hercules Corona Borealis Great Wall, a structure so massive it spans 10 billion light-years, nearly a seventh of the observable universe. According to conventional physics, nothing that big should exist. Gravity wouldn't have had time to assemble it. But what if it's not a product of our universe alone? A brain collision could have dumped energy into space like a stone tossed into a pond, creating shockwaves that funneled matter into these improbable superstructures. It's a fringe idea, sure, but one that gains traction when you consider oddities like the cold spot, a void in the cosmic microwave background so enormous and frigid that some theorists propose it's the echo of another universe nudging ours long ago. Even the web's geometry fuels speculation. Simulations show filaments should twist and fork like tree roots, yet some observed strands are eerily straight, as if stretched by forces we can't see. Could these be cosmic tethers, regions where another universe's gravity subtly tugs on ours, or consider dark flow? the mysterious drift of galaxy clusters toward a single point beyond the horizon. Mainstream cosmology chalks it up to primordial fluctuations, but what if it's the gravitational pull of a neighboring brain, invisible but undeniable? Of course, not all multiverse theories are so dramatic. Quantum mechanics suggests every decision spawns alternate timelines, branching endlessly like threads in a tapestry. In this view, the cosmic web might be a nexus where probabilities crystallize, each filament a highway where certain realities grow dominant, while others fade into the voids. It's an intoxicating thought that the web's structure isn't just shaped by dark matter, but by the weight of infinite possibilities. Skeptics argue these ideas are untestable, more philosophy than physics. Yet, instruments like the James Webb Telescope keep finding anomalies, filaments too hot, voids too empty, that resist conventional explanations. Maybe the truth lies in the gaps. After all, humanity once laughed at the idea of invisible matter until dark matter upended cosmology. Who's to say the web's next revelation won't be even stranger? Whether cosmic accident or multiverse graffiti, one thing's certain: the deeper we map the web, the more it feels like we're reading someone else's blueprint. And the handwriting doesn't look familiar. The cosmic web might be the universe's greatest architect, not just of galaxies, but of the very conditions that make life possible. Picture a galaxy adrift in one of the web's dense filaments, bathed in a steady stream of gas and cosmic raw materials. It's like a city built along a fertile riverbank where resources flow abundantly, nurturing stars and planets. But just as crucial to life's odds are the voids, those vast, empty regions where galaxies are few and far between. While they might seem like cosmic deserts, their emptiness could be the universe's way of shielding fledgling worlds from catastrophe. A galaxy tucked into a quiet corner of a void avoids the violent collisions and radiation storms common in crowded filament hubs, giving fragile planetary systems the stability they need to cook up chemistry over billions of years. This delicate balance between abundance and isolation might be the secret recipe for life. In the dense filaments, galaxies feast on gas, birthing stars at a furious pace. But too much density brings danger. Galactic collisions rip apart orbits, supernova sterilize nearby systems, and black holes spew deadly radiation. On the other hand, a galaxy stranded in a void might starve, its gas reserves too sparse to ignite new stars, leaving planets frozen and lifeless. The sweet spot, a filament's outskirts where galaxies get enough fuel to thrive but remain buffered from the chaos of the core. Our own Milky Way sits in such a Goldilocks zone, close enough to the local filament to draw resources, yet shielded by the local void's emptiness from the chaos of superclusters like Virgo. The web structure also plays matchmaker for life's building blocks. Heavy elements like carbon and oxygen, essential for planets and biology, are forged in stars and scattered by supernova. In filament environments, these elements recycle efficiently, swept up by gas flows and funneled into new stellar nurseries. Voids, by contrast, might trap galaxies in poverty, their stars burning clean but leaving little behind to seed future generations. Yet even voids have their role. Their sparse landscapes could preserve rare, ancient systems, cosmic time capsules where life, if it arose early, had uninterrupted eons to evolve beyond our imagination. The debate isn't just academic. Telescopes like James Webb are now spotting exoplanets in galaxies both dense and isolated, offering a real-time test of these ideas. Some theories suggest filament galaxies, rich in metals and energy, are life's powerhouses. Others argue void galaxies, with their calm and longevity, could hatch more advanced civilizations. The truth might lie in the web's grand Chinese letter, where structure and emptiness conspire to create pockets of possibility, a universe not just built to endure but to awaken. Data and beauty collide when artists transform the cosmic web's invisible architecture into breathtaking visuals, turning trillions of data points into something you can feel. Take NASA conceptual illustrator Dana Berry, who stitches together telescope scans and supercomputer models to create renderings so vivid they've gone viral on social media. Her work isn't just pretty, it's a translation, converting the cold math of dark matter distributions into swirling rivers of light, their golden filaments pulsing against the void like neon synapses in a cosmic brain. The genius lies in the details. Galaxies cluster like fireflies along each thread, their glow tinted by age, blue for youthful stars, red for ancient giants, while voids yawn as bottomless indigo chasms. These aren't mere artist impressions, they're grounded in petabytes of real survey data, polished to reveal truth raw numbers could never convey. This fusion of art and science does more than dazzle, it democratizes. When the European Space Agency released a 3D fly-through of the web's filaments, viewers didn't just see structure, they soared through it, diving past galaxy clusters and skimming tendrils of gas like intergalactic surfers. Suddenly, abstract concepts like large-scale structure became visceral experiences. Social media lit up with comments like, "I finally get dark matter." Proof that a well-crafted visualization can bypass jargon and land directly in the gut. Even astrophysicists admit these artworks sharpen their intuition. Simulations might show a filament as a spreadsheet of densities, but watching it twist in holographic form, that sparks new questions about why certain strands kink or fork in unexpected ways. The viral potential is undeniable. Instagram accounts like @Cosmic Background amass millions of likes by pairing web visualizations with minimalist captions. "This is where you live." TikTok creators layer them with ambient soundscapes, turning void-crossing journeys into asthma-like immersion. Meanwhile, exhibits like the Hayden Planetarium's Dark Universe drop audiences into real-time simulations where filaments grow like roots across the dome overhead. The effect is humbling, a reminder that humanity's entire history occupies less than a pixel in this grand design. But the real magic happens when art exposes science's blind spots. Artist Kim Albrecht once mapped the web using only gravitational lensing data, rendering it as a delicate mesh of white threads on black, the result. A haunting fragility. No graph could capture threads so thin they seemed moments from snapping. Astronomers paused. Had they underestimated dark energy's erosive power? Others, like musician-turned-visualizer Matt Russo, sonify the web, assigning musical notes to galaxy densities. Played back, the cosmos hums in chords both harmonious and dissonant, echoing how filaments harmonize matter, or sometimes defy expectations. These collaborations are rewriting outreach. When NASA James Webb team needed to explain cosmic reionization, the era when the web's gas first lit up, they didn't default to a lecture. They commissioned an animated short from Studio Momo, showing ultraviolet bubbles blooming along filaments like fairy lights flicking on in sequence. Within days, educators worldwide were using it to teach high school physics. That's the alchemy here. Take science's driest data, filter it through an artist's lens, and watch it ignite wonder in minds of all ages. Because understanding the cosmic web isn't just about charts, it's about feeling, even for a heartbeat, like part of something vaster than thought itself. Some argue that pouring billions into mapping the cosmic web is a luxury we can't afford, not when Earth faces climate crises, poverty, and pandemics. Why launch telescopes when hospitals need funding? Why simulate dark matter when cities flood? It's a fair question, but here's the irony. The same tools built to decode the universe's secrets are already saving lives down here. Take the algorithms developed to sharpen Hubble's fuzzy images of distant filaments. Those same techniques now detect early-stage tumors in MRI scans, spotting anomalies human eyes might miss. Or consider CCD sensors invented for astronomy to capture faint starlight, now omnipresent in medical X-rays and smartphone cameras. The list goes on. GPS relies on relativistic physics fine-tuned by observing pulsars, while climate models borrow code from simulations of interstellar gas clouds. Cosmic curiosity doesn't just gaze outward, it retrofits our world. Then there's the intangible payoff perspective. When the Apollo missions beamed back the first whole Earth photo, that fragile blue marble suspended in blackness reshaped humanity's self-image overnight. Pollution knew no borders, conflicts felt smaller. Mapping the Cosmic Web offers a sequel to that revelation, a humbling reminder that all nations share not just a planet, but a galactic neighborhood woven into the same dark matter threads. Projects like the Square Kilometer Array Telescope unite scientists from warring states, collaborating across political trenches to piece together the web's structure. In an era of fragmentation, these quests forge rare common ground. Critics still ask, shouldn't we fix Earth first? But history shows exploration and survival aren't rivals, they're partners. The Renaissance navigated plagues and wars while funding telescopes that unlocked the heavens. Today, decoding the web's structure could reveal existential threats, like rogue galaxy clusters on collision courses with our local filament. Or it might uncover energy sources lurking in the quantum foam of spacetime itself. The line between useless cosmology and civilization-saving tech has always been blurry. After all, Einstein's equations seemed abstract until they powered GPS and nuclear medicine. The real risk isn't investing in cosmic maps, it's cutting them short. Every time we've prioritized immediate needs over fundamental discovery, we've missed revolutions. When Britain slashed funding for pure math in the 1800s to focus on industry, they never imagined those abandoned theories would one day encrypt the internet. The web above mirrors the web within. Pull one thread of curiosity and you might unravel 1,000 earthly problems. So yes, heal the planet, but remember, the stars have handed us bandages before. Every atom in your body, the calcium in your bones, the iron in your blood, even the carbon fueling your thoughts was once stardust, forged in the heart of a galaxy far from here. And not just any galaxy, but one threaded along the cosmic web's vast filaments, where swirling clouds of gas collapsed into stars that lived, died, and exploded, scattering their elemental ashes across the universe. That oxygen you're breathing right now, it was likely born in a supernova that detonated billions of years ago. Its shockwaves funneled along a dark matter filament until it found its way into a molecular cloud, then a protostar, then a planet, and finally your lungs. You're not just a bystander to this cosmic architecture, you're a product of it, a living testament to how the web's invisible currents shaped everything. Think about the screen you're staring at. The silicon in its circuits, the aluminum in its casing, they're cosmic immigrants too. Their journey began in ancient galaxies that no longer exist, their atoms hurled into the void by collisions or stellar winds, only to be swept up by the Milky Way as it orbited the web's gravitational currents. Even the gold in your jewelry was likely created in a cataclysmic neutron star merger, its precious atoms ejected into space until they were caught in the web's filaments, drifting for eons before reaching Earth. The web isn't just out there, it's in here, woven into the fabric of your being. This connection stretches back further than you might realize. When the universe was just a few minutes old, the only elements were hydrogen, helium, and trace lithium, the raw materials of the cosmic web's first strands. Everything heavier, from the carbon in your DNA to the nitrogen in your proteins, was cooked up later inside stars, then scattered across the cosmos by supernova and stellar winds. Without the web's filaments to channel and concentrate these elements, they might have dispersed into the voids, leaving planets and life impossible. You exist because gravity's invisible fingers gathered stardust into fertile pockets where chemistry could experiment for billions of years. Carl Sagan famously said, "The cosmos is within us." We are a way for the universe to know itself. It's more than poetry, it's physics. The same forces that sculpted galaxies from primordial gas also sculpted you. Every time you feel the sun on your skin, you're sensing energy from a star whose birth was guided by the same web that cradled our own. When you look up at the night sky, you're not just observing the universe's structure, you're seeing the branches of your own family tree, etched in light and dark matter. So next time life feels small or fleeting, remember, you're not just on this planet, you're of it, and of the vast star-strewn web that binds all things. That's not just science, it's a story written in every cell of your body, waiting to be told. We've traveled from the smallest filaments of dark matter to the largest voids in existence, tracing a structure so vast it defies comprehension. A cosmic skeleton stretching over 93 billion light-years, woven from the births and deaths of galaxies. This isn't just science, it's a detective story where the clues are bent beams of starlight, ghostly neutrino signals, and supercomputer recreations of the universe's infancy. Every tool in our arsenal, from Hubble's keen eye to quantum algorithms humming in sub-zero labs, has pulled another thread from the darkness, revealing a web more intricate than we ever imagined. Yet for all we've uncovered, the thrill lies in what remains hidden, the nature of dark matter, the true face of dark energy, and whether the web's grand design holds keys to realities beyond our own. The beauty of this quest, you don't need a telescope to join it. Step outside on a clear night and you're already gazing at the web's glittering nodes, the Milky Way's arc, Andromeda's smudge, the Virgo cluster's distant glow. Every stargazer becomes a cartographer, tracing the same filaments that birthed our atoms. Prefer pixels to stars. Citizen science projects like Galaxy Zoo let anyone classify galaxies from their couch, uncovering cosmic threads professionals missed. Coders can dive into open-source astronomy datasets, hunting for patterns in the noise. Artists can render the unseen, turning quasar spectra into music or dark matter distributions into murals. The cosmic web doesn't belong to scientists alone, it's humanity's shared inheritance, a story written in gravity's ink, waiting for fresh eyes to read it. As for what's next, the web keeps surprising us. New telescopes like the Vera Rubin Observatory will map billions more galaxies, while experiments like LUX Zeppelin hunt for dark matter's elusive particles. Maybe one day we'll grasp why filaments twist the way they do, or why voids repel galaxies like opposite magnets. Perhaps we'll even find proof that our web brushes against others in dimensions we can't see. But this much is certain: every discovery peels back another layer, showing us that the universe isn't just stranger than we imagined, it's stranger than we can imagine. So keep looking up, keep questioning, keep sharing the wonder. Whether you're pointing out constellations to a friend or coding an AI to simulate dark matter, you're part of the greatest exploration in history. The universe's skeleton is hidden no longer.